Now it's official. There we go. So yeah, thanks, Jane. I'm going to go ahead and get my screen going here, and then we'll be able to kind of look at some pictures here, go through a couple things. I spent some time preparing this for you. Yeah, happy to be here. Thank you, Jane, for the introduction. And I hope to convey some information this evening that everyone will find interesting, whether you're from Stanley, Idaho, or you're from another location, just to give you a little bit more information about the really amazing and complex and really fascinating geology we find in central Idaho. I thought this would be especially of interest to the folks in the Stanley area. We're going to look tonight at the role in which glaciers and earthquakes have played in central Idaho, two pretty beefy topics that we could spend quite a bit of time on. We're going to mainly focus on the Sawtooth Mountains and an adjacent or nearby mountain range. And then we're going to look back at the March 2020 earthquake, which I know some of you experienced kind of at ground zero there in the Stanley area. But this is our sort of like first shot here. And I think this nicely encapsulates the things I'm going to talk about this evening. This is a view to the west of the main Sawtooth Range from the Boundary Creek trailhead, or a ridge just above it anyway. And, you know, as you look at this iconic landscape and skyline of mountains here, you're really looking at the culmination of these two very powerful and profound geologic process. And that is the earthquake activity, which has caused the uplift of the Sawtooth Range, along with other ranges in Idaho. And then the glacial erosion and deposition, which has beautifully sculpted the skyline and the high peaks in the Sawtooth. So if there's two processes that folks in that area should maybe know a little bit more about, or appreciate, or come to appreciate anyway, that would be it. Since I'm hoping to interest people in learning more about Idaho's geology, I thought, and she did mention some of these in the bio there, but I thought I'd just make a quick plug and also just tell you a little bit more about these two geologic resources I've been involved with. So the first one here, the Geology Underfoot in Southern Idaho book, is a book that covers everything from just north of Stanley south in the state of Idaho. And it more or less picks 23 locations where I thought there was just a really compelling and interesting geologic story. And this series is actually a series from Mountain Press Publishing in Missoula, Montana. This series of books, Geology Underfoot, basically asks people to kind of get out of their car, engage with the landscape in some way, shape, or form, maybe looking at a vista, a road cut, might be a trailhead, might be any sort of landscape feature, but nothing too far away, no death marches to the top of a peak or anything like that. But getting people out of their cars, engaged with the landscape, and then by asking questions and asking people to observe certain things, it explains the geologic history of those locations. So that book was published in 2017. It's available through me, but also on Amazon, and like it's at libraries and local places in Southern Idaho as well. And then just a year or two ago, I was involved with a project to redo the Roadside Geology of Idaho book. Some of you might be familiar with the first edition, which was published in 1988. Some years had gone by since 1988. We had since learned a lot more information and new ideas about how the Idaho geology kind of came to be over time. And so myself, along with two other geologists in the state, put together this Roadside Geology book for the whole state. And so this book's a little bit different. Instead of in-depth stories at specific locations, this book tells you a little bit about the geology you're driving by along Idaho's highways and freeways, and a few of the backways and scenic roads as well. But it's more a highlight reel. It's just telling you, hey, milepost 213, if you look off to your left, this is what you'll see. And then it kind of moves ahead to the next landform or feature along that highway or roadway. So two books that are out there, at least among the books on Idaho geology. So nice resources if you're interested in learning more. And then, as Jane mentioned, I also have put together a YouTube channel. And this is something that came about during the pandemic. I was looking for ways to bring field trips and geology to my students that I then couldn't meet with because of COVID. And so what started as a project to just maybe showcase a few locations to my students turned into a sort of conduit to reaching a much bigger audience. And so I had no idea at the time. I thought, maybe a couple people would get on this thing that were interested in Idaho geology. But what I really found was there's this huge community of people out there, not just in the US, but globally even, that was interested in not just Idaho geology, but just geologic processes in general. So there's a number of videos on here. Some are explaining different rock types. Some are about specific locations. There's a lot in Idaho, but there's a lot in other places as well. And as I get out and travel around and see interesting places, I try to put together more videos. So that's something that you might also look toward. So, and then lastly, before we get started here, I just want to give a quick thank you to some individuals who helped with this presentation. As I thought of my topic and what I wanted to cover this evening, it became grossly and tragically apparent that I didn't have a lot of the photos that I would have liked to have had. I am not a good photographer, and I often don't take pictures when I'm out doing things. And yet I wanted to show you some interesting features geologically in these mountain ranges in central Idaho, and I realized I just didn't have the photos for it. So I reached out to some groups on Facebook that I knew were big fans of the Lost River Range and the Sawtooth Mountains in particular, and I'm just really appreciative of those folks who were able to generously provide their photos to share with me, to share with you tonight. And I've credited all those fine folks at the bottom of their photos. So appreciate those folks. So let's get started. We're going to do two different things here tonight. We're going to focus on the glaciers first, and then we'll kind of have a transition, and then we'll go into the earthquake. So it's a bit of two different topics and two separate presentations, but the common theme is the area and the location that we're investigating tonight. So before we get too far into glaciers, I thought it might be worthwhile to look at just how glaciers form and what the recipe is, and how they modify the landscapes over time. So if we think of glaciers as starting with snow, if you look in the top right diagram here, snow, which is composed of little crystals of water, of course, frozen water, a lot of it's actually air. Even within the crystalline structure, a lot of that material is air. But as that snow gets compacted over time, it actually breaks down from its very kind of pretty snowflake crystalline structure and eventually becomes just kind of a tiny little ice pellet. And so the amount of air in that material decreases as it gets compacted and as more material accumulates. And so if you can get snow to accumulate in any given location persistently, and it takes typically hundreds, if not thousands of years to really kind of grow a glacier in most instances, if you can get that snow to slowly be transformed into glacial ice, and if it has sufficient mass, that ice will then start to move down slope under the influence of gravity, and voila, you have a glacier. You've got a glacier on your hands. There's oftentimes some confusion about what a glacier is or isn't. Sometimes people hike up into the mountains in August and they see a white patch on the hillside, and they assume it's a glacier, when in fact it's just maybe a persistent snowfield, depending on how much snow we're getting in a given year. In Idaho, we preferentially see glaciers forming on north or northeastern slopes, and that's because those sides of the mountain or the topography are going to be protected from the afternoon sun. It's obviously much easier to grow your snowfield into a glacier if it's somewhat protected from the sun. If it's facing south or facing southwest, it's much more difficult to get glaciers, at least in Idaho, to form. Now, obviously, if you have enough snowfall, or if you go further north into Alaska or Canada, you're at such a high latitude and it's cool enough that the sun isn't as big of a factor, and you can indeed get those glaciers forming on different slopes with different aspects. And so in the diagram here at the bottom left, we can see just a diagram of a glacier. And the place at the top of the glacier, up to the top of the mountain, that's the area where we actually add more mass, more snowfall, which turns into ice that sort of feeds the glacier. That's what we call a zone of accumulation. Of course, as the glacier slides down to lower elevations where it's warmer, that's where the glacier is going to lose some of its mass. And this is what's sometimes called the zone of wastage, or sometimes it's called the zone of ablation. It's basically where we're losing mass. It could be evaporation. It could be melting, obviously, into water, evaporation of that water, or it could be sublimation, where we're turning that ice directly into water vapor gas without actually melting it into water. And in any given glacier, it's kind of a checks and balances, right? So you've got added material at the top and loss of material at the bottom. And it really just depends on the given sort of climate from year to year or decade to decade as to what this glacier is going to do. If it's adding more mass at the top than it's losing at the bottom, then it will move further down and it will advance across the landscape. If, on the other hand, it's losing more at the bottom than it's adding at the top, then the glacier will retreat over time. So it's kind of like, I guess, in a way, it's kind of like your checkbook. You know, if you're saving more than you're spending, then your bank account grows. And if you're spending more than you're saving, then your bank account dwindles. And that's not a good thing. And so that's basically, in a nutshell, just a brief overview of kind of how glaciers form and behave. And there's obviously a lot more detail than that, but hopefully that will suffice. So the main thing that glaciers do in any given landscape is they sort of do two things, and they do them actually simultaneously, but just in different locations. So at the top of the glacier, up in the mountains, in the high peaks, that's where the glaciers do most of their erosion. So that's when the glaciers are actively shaping the landscape by grinding down rock, removing bedrock from the underlying topography, and incorporating that broken, eroded material in the ice itself. So thinking of a glacier as just ice is a bit too simplistic. The glacier actually also has embedded rocks, sand, even tiny clay-sized particles encased in the ice. And those particles can come from a couple of different sources. They can come from rocks falling onto the glacier from the adjacent cliffs. It could be as the glacier slides over the rocks beneath it, the ice can actually pluck and remove rocks that are beneath it. And so those become entrained in the ice as it slides down. But the wonderful thing about this process is it creates some very telltale signs and landforms that we see in a glaciated area. So here we have a picture at the top here of Sawtooth Lake. And we can see, looking to the south here, near Mount Regan, this beautiful U-shaped valley. So glaciers are notorious for turning V-shaped valleys, which are formed by streams and rivers, into much broader U-shaped valleys as the glacial ice passes through that area. We can also see, if you look in the sort of the top right corner of that photo near Mount Regan, you can see a very narrow ridge line, a narrow divide between this basin where Sawtooth Lake sits and whatever the adjacent basin is just to the right. So these are these narrow ridge-like features we call arêtes. There's another photo of one here in the bottom left corner. And this is really where the Sawtooth name really kind of comes into its own, is the glaciers and these knife edge ridges, these arêtes, form this sort of serrated skyline that people see from the valley floor that kind of gives the Sawtooths their name and the reason we kind of name them. This bottom right photo is a beautiful picture up in Redfish Canyon of glacial polish and glacial striations. And so you can see these just beautiful lines on the photo here going left to right horizontally as the glacial ice progressed down the valley. That grit encased in the ice actually not only scoured the rocks below, it actually polished it. This is actually the start of a climbing area called super slabs. And the trickiest thing about climbing up this thing is staying off of the kind of lighter colored material, which is exceptionally slippery and polished and difficult to use as hand or footholds, and putting your feet on these darker blotches here where some of that glacial polish has been weathered through, and you get the granite underneath, which is much more gritty. So just beautiful examples. The bottom left photo is looking north from the trail up to Sawtooth Lake. So nice examples in the high country of glacial erosion. As we move down into the valleys where the glaciers end up, this is where the deposition takes place. So as the glacier advances down into the valleys, now we're entering a region where the ice is melting, the ice is sublimating, it's warmer. And so all that grit and sediment, the boulders, any rocks that are entrained in the ice will get deposited on either side of the glacier and at the leading edge of the glacier. And these are what we call moraines. And so moraines are these ridges of deposited glacial material, which we call till. The bottom right photo just shows a nice typical example of glacial till. It's just a hodgepodge mixture of anything the glacier can carry, and glaciers can carry just about anything. They're incredibly large and powerful. You could put a rock the size of my college campus on the back of a glacier, and it would have no problem transporting that down slope. So a real mixture of big and little rocks, typically kind of angular, but they might be a little bit rounded, but the glacial ice itself doesn't round the rocks. The bottom left photo, you can see a ridge of till, of sediment on either side of this lake here. And so if you sort of imagine this now on the landscape around the Sawtooth, I think you can start to see what we had here only a few tens of thousands of years ago. So we're going to focus on the central mountains of Idaho, and I've highlighted a few of the mountain ranges here, but there's two in particular we're really going to spend time on. So just for reference, for those that might be not from this part of Idaho, we've got Boise over here in the lower left corner, the lava fields of Craters of the Moon near the lower right corner, and then this just incredibly mountainous region that forms the central sort of heart, if you will, of the state of Idaho. Of course, we've got many folks in the Stanley area, and Stanley sits at the base of the Sawtooth along the Salmon River, and right at the foot of these big mountains here. So we're going to focus much of our time tonight on the Sawtooth. We've got the White Cloud Mountains here, the Pioneer Mountains here, the Lemhi Range off to the east, but we're also going to focus on this big mountain range here, the Lost River Range, LRR, Lost River Range. And this has the highest peak in the state with Bora Peak. So these two mountain ranges, along with others, form some of the most dramatic and captivating scenery that we have in all of Idaho. Both of these mountains are formed by uplift on one side of the mountain range caused by a large active, what we call an extensional fault or normal fault. So in the Lost River Range, that big fault lies on the southwest side or the west side of the range. That's the same fault system that produced the 1983 Bora Peak earthquake, which is the largest historical earthquake in Idaho. At the Sawtooth, our big fault lies on the east side of the range. It's called the Sawtooth Fault, and it's the one that was responsible, at least we think, for the March 2020 earthquake that we had just a few years ago. So in a way, we'll circle back to that. So despite the similarities we see with these two kind of lofty mountain ranges, there's some real distinct differences in their glacial histories that I want us to explore here a little bit. So here's a nice summary of these two mountain ranges. And I want to kind of present this in a way, I want to present this a bit as a riddle or a little bit of a mystery. And it's not like a complicated riddle. Some of you might be able to figure it out already, but I'd like to walk you through some of the evidence, show you some nice photos as well. And then let's see if we can come to a reasonable conclusion as to why we see some vast differences in the glacial history of these two mountain ranges. So in the Sawtooth, we've got high peaks that go up to 9,000 or 10,000 feet or so. On the Lost River Range, it's taller. It's a good couple thousand feet taller than any of the peaks in the Sawtooth. So we have mountains that go into the 11,000 to 12,000 foot range. The Sawtooths are easily, by far, much more extensively glaciated on both the east and the west sides of the mountains. They show evidence for large, very thick glaciers that extended from the high peaks all the way down to the valley floors, down to an elevation of about 6,500 feet. If you spend some time in the Sawtooth in the high country, you know that one of its beautiful characteristics are the alpine lakes. There are just probably hundreds of these high alpine lakes up in the high country of the Sawtooth. And we also have lakes down in the valley as well, behind some of those moraines that we'll look at. If we contrast that with the Lost River Range, like we said, it's way less glaciated. It has glaciers, but they tend to be just on the east side of the range. And those valleys that had glaciers in them, it looks like those glaciers didn't get nearly as far down the valley floors. And so they terminate at a much higher elevation than what we see in the Sawtooth. And then finally, if you look around the Lost River Range, there's a few lakes here and there, but you could count them on, a couple hands, I suppose. I haven't counted how many there are, but I would guess there's, maybe 10, 20, 30 or so. And they're small. They're not nearly as big as the lakes we see in the Sawtooth Range. And so think about this as we look at some photos here. Think about this interesting contrast between these two mountain ranges. On one hand, we've got the higher peaks, but less of an impact of glaciers and smaller and fewer lakes versus a much smaller mountain range that shows signs of being extensively glaciated with lots of lakes. So let's look at some nice images here that might help a little bit. This is the topography of the Sawtooth. So here's Highway 75 coming from Stanley and Ketchum up over Galena Summit. And then Stanley would be, a few more miles to the north here on the highway. And we've got the Sawtooth Range over here on the left side of the image. And what you can see here is just several spectacular glaciated features. At the high peaks, we can see a lot of these bowls, what we call a cirque, a glacial cirque. This is a place where the ice began for the glacier as it moved down slope. It excavates a sort of depression or a bowl in the high peaks as the ice moves down. And of course, these depressions then become ideal locations for water to accumulate. And that's where we get a lot of these high elevation lakes in the Sawtooth. As we work our way down, though, these alpine valleys, we can see these just beautiful ridges of sediment. This is the glacial till. This is the moraines that formed in these places. So here we have Alturas Lake, Yellow Belly Lake, that's what Pettit Lake, Hell Roaring Lake up here. These are all lakes that are present because they sit in this low depression surrounded or encased by these moraines. So at one point we had these big glaciers advancing all the way out onto the Stanley Basin floor. And in some instances, as you can see here with the glacier that was at Hell Roaring Creek, its moraine comes all the way out and actually somewhat dictates the path of the Salmon River. So the Salmon River has had to change its flow path and channel over time as these glaciers advanced and withdrew. Now, when we look at these moraines here, these kind of rubbly, irregular areas at their terminus, at the end of the lobe, that tells us how far the glaciers extended at their maximum. So the glacier would have come down, retreated. It was a kind of constant just up and down movement of the glacier back up its valley, or back up into the mountains, down into the valley. But this furthest extent here is recorded by the moraines over time. So that's what it looks like sort of as a specific type of map view. This is what it looks like using Google Earth. So there's Highway 75 in the foreground, north is to your right. And some of those same lakes we just looked at, we can see those here, but then we can beautifully see these glacial moraines. In fact, the trees tend to prefer the glacial moraines because they contain a mixture of sediment sizes and soils that are pretty well drained. So they get their water and there's more nutrients in these soils on these moraines versus the valley floor, which has a lot of clays and some other material in it that make the trees a little bit harder to grow in. So just spectacular view there looking to the west at the Sawtooth Range. Here's what it looks like from the top, kind of looking down from the crest of the Sawtooth. This is near Thompson Peak, looking down at one of these beautiful cirques, one of these glacial depressions in the high country where the glacier started. This one's occupied by a small, probably unnamed lake. Maybe it has a name, but I'm not sure of what it is. And then you can see as the ice would have flowed down the valley here, you can start to see some of these ridges at the top of the photo, kind of in the haze there. Those would represent the moraines as this glacier came down into the valley down here towards Stanley. Another quick view of the Sawtooth. This is Goat Lake, a real favorite hiking destination for a lot of people. Again, kind of showing the steep walls that surround these cirques, some of those knife edge ridges in the distance. So the arêtes there. This one also occupied by a lake. And then this one we can also see, this was just sort of extra fun for me and maybe for you, is this dark stripe cutting through the granite at the head of Goat Lake, which is a dike. So this is a fracture that magma moved through probably during the Eocene about 50 million years ago, that's filled in with some darker igneous rocks. So really nice shot there of Goat Lake. So now that we've looked at the Sawtooth, let's head over to the Lost River Range and make kind of a similar comparison. So here's Highway 93 in the bottom left corner. If you head down to the south on that highway, you'll end up in Mackey and Arco, Craters of the Moon. If you head to the north, you'll end up in Chalice, where if you wanted to, you could get onto Highway 75 and head towards Stanley. We can see the ridge lines. Remember, this is the higher mountain range, but as we look at it, we can see it's not nearly as extensively glaciated. It does have nice cirques. If we look at these little rounded depressions at the high peaks, we see that there's quite a few of those. There's a couple lakes in there, but we do not see much in the way of moraines. And I know I kind of cut this off. I probably should have amended this a little bit. I'll show you some photos looking down some of these valleys, but these glaciers didn't go very far, and they definitely didn't cut down into the landscape as extensively as the Sawtooth glaciers. What's more, you can see that here's the ridge line of the Lost River Range, and notice that there are no cirques for the most part or glacial evidence on the west side of the Lost River Range. And so whatever snow was accumulating here was not accumulating thick enough, and the ice wasn't becoming thick enough to form extensive glaciers at all on the west side for the most part. And even coming down these valleys on the northeast and the east sides of the range, the glaciers are just a lot smaller than what we see in other places. Let's look at some actual photos then here. So here's Bora Peak. That's our tallest point in Idaho, 12,000, what is it, 662 feet, something in that range. And on the east side, again, a nice, beautiful glacial cirque. You can see the rocks here are quite a bit different than what we see in the Sawtooth. Rather than these hard granitic rocks, what we have in the Lost River Range are layered, bedded, sedimentary rocks. These rocks are largely from the late part of the Paleozoic era, so they're around 340-ish million years old. And this is mostly limestone with some beds of sandstone in here. So these rocks actually were deposited at the bottom of the ocean, or in some cases like a beach environment. And now they form the loftiest peaks in the state. And a lot of these limestones have fossils in them as well. But you can see this beautiful cirque here with a small lake. This is a great shot here looking down off Bora Peak down to the east. So you can see the U-shaped valley. That's probably that same lake we just looked at, I'm assuming. U-shaped valley, a nice wide glacial valley here. And then it kind of turns out to the left. And if I had a little bit more of this shot here, which I apologize for, the moraines aren't as nearly as obvious in the Lost River Range as they are in the Sawtooth, presumably because the glaciers were much shallower. You can see that we don't have like a good scale here, but that valley, that U-shaped valley, is much broader and not nearly as deep as some of the canyons we get up in the Sawtooth. And so we could make some measurements here and some guesses as to how thick the ice was. And I think we'd come to the conclusion that these Lost River Range glaciers had substantially much less ice in terms of total thickness of the glacier itself. Here's another shot. This is from near Leatherman Peak, showing some of there's a nice cirque over here on the left side, a nice bowl-shaped depression for ice to accumulate, coming down these glaciated valleys here. But we're at the high peaks here. We're at 12,000 feet looking at these. And by the time you get a little ways down these valleys, the glacial evidence starts to really taper quite a bit. Again, a tiny little lake here, but again, pretty dry in the Lost River Range. I think if you even look at the vegetation and the trees, there's some stark differences there as well, but I'm not as well informed on that, so I won't speculate. The other nice thing we can see here is how beautifully folded some of these sedimentary rocks are in the Lost River Range. Just above this lake here, in the foreground, you can see a beautiful downward bending fold. We call that a syncline. So these layered sedimentary rocks, which were once at the bottom of the ocean, have just been beautifully folded by a previous mountain building event, not the mountain building event that pushed these mountains up, but previously during the Cretaceous, about 70, 80, 90 million years ago, there was another mountain building event that caused these rocks to be deformed. One more look. Now we're going to go over to and look down the west side of the Lost River Range. So this is near Mount Breitenbach. We're looking towards the White Knob Mountains there to the west. There's Mackey Reservoir in the middle ground. And you can see that these west side canyons are more V-shaped, more like the type of shape we would expect to see from water erosion versus glacial ice. So even up here above tree line, where the skier is enjoying the snow, late spring snow here, we just didn't have enough persistent snow to form glaciers during the last ice age 20,000 or so years ago. Okay, so that's what the Lost River Range looks like. So I'm going to summarize it all here. So hopefully I've intrigued you a little bit. If nothing else, maybe entertained you with some nice scenic photos. But remember, what's our conundrum here? Our big dilemma is we've got the bigger mountain range here with much higher peaks. So if we assume that the main control on glacial extent and the thickness of the ice on a glacier is primarily elevation, which is a factor in many places. Typically, as you go higher into the mountains, you get more snow, therefore you can get bigger glaciers. But here in central Idaho, that seems to be not the case. We have the taller mountains here in the Lost River Range that are far less extensively glaciated than the much smaller Sawtooth Range over here. So maybe you figured it out, maybe you haven't. So here's a big clue to this dilemma. What we're going to do is we're going to pick 3 locations, 3 towns, Stanley, Mackey, and Lador, and we're going to look at their snowfall amounts. And so comparing these 3 locations, these towns' snowfall amounts, I think will reveal what I think is the dominant control on the extent of glaciation in these locations. So over here in Stanley, at an elevation of about 6,200 feet, that's the elevation of the town more or less, they get on average, in some years they get more and some years they get less, about 76 inches of snow on average in Stanley. If we move over here to Mackey, similar latitude, similar elevation, we see that the snow drops almost in half here, 33 inches per year on average in Mackey, 6,000 feet. If we come over here to Lador, which again, similar latitude, similar elevations, they only get about 18 inches of snow per year. So what we have here is we have a strong rain shadow component. As these storms come in primarily from the west or the northwest, the first thing they run into, the biggest formidable mountain range they run into, is the Sawtooths. And the Sawtooths therefore get a lot more snowfall. Much of the moisture from these storm systems falls over the Sawtooths. As it drifts over here, and this isn't very far, this is maybe maybe 50, 60 miles from one mountain range to the next. As they get over here to the Lost Rivers, they've got a lot less moisture, and so they drop less snow. And by the time they get over the Lemhi Range, another big mountain range with 11, 12,000 foot peaks, into the next valley over here by Lador, they have even less snow or moisture to fall from the sky. So what we have then in central Idaho, and you really can see this just with the Google Earth image, look how green it is on the west side of the Sawtooths. And as you just move across this image, it gets brown really quick. The green is everywhere in the Sawtooths, except where it's white there in the high peaks with the rocks. But there's not a lot of green in these valleys here around the Lost River Range. So we have sort of I guess it's a double, maybe triple whammy snow rain shadow effect, where we have the Sawtooths, the white clouds, which are up to 10, 11,000 feet. Those suck some of the moisture. And by the time these storm systems get to the eastern part of the state and the Continental Divide in Montana, they've dropped a lot of their moisture in the central part of the state. So I hope you found that compelling. I've always found that a cool story and just a neat little explanation for why we see much more extensive glacial features in the Sawtooths, even though they're a smaller mountain range compared to some of these other loftier ranges. So I'm going to switch gears here and now talk about earthquakes. And so we're going to focus rest of our time here on the March 31st, 2020 Stanley earthquake, which had a magnitude of 6.5. So it was a large earthquake. It was felt not just in central Idaho, but in the surrounding region, hundreds of miles away. My embarrassing fact is that here I am in Twin Falls, not too far away, and a lot of people in Twin Falls definitely felt the earthquake. but I did not. At the precise moment that the earthquake shook Twin Falls, if you remember, this is just when the pandemic had kind of set in and we're all just sort of trying to not go stir crazy. Our family was going to do a yoga session over Zoom, and I was downstairs pushing the sofa across the floor to get it to the other side of the room at the same moment that the shaking was felt. And so during those few seconds of me pushing the couch across the room, I was completely oblivious and did not feel the earthquake. And my family was screaming upstairs, and I ran upstairs and I could see the light fixture above our dining table swaying. And so that was my first indication that something had happened. And then, you know, the phrase that people often say that your phone blew up, because I'm the only geologist a lot of people in my family and my friends know, my phone literally blew up with text messages, just all sorts of people saying, was that an earthquake? Did you feel it? And so it was a busy couple of days, but an exciting couple of days. So here's Stanley here. Here's the Sawtooth and the two highways, Highway 21, Highway 75, and the epicenter, the actual location where the rocks broke and shifted across a fault, was up here near Cape Horn. This is where Highway 21 kind of swings around and almost does a 180 here. So it's, you know, maybe 15, 20 miles away from Stanley. Happened at about 5:52 local time. It was a shallow earthquake, about 9 miles or 14 kilometers in depth. So that meant that a lot of the shaking was effectively transmitted through the crust to neighboring communities. So we felt more or less the full power of this earthquake. Obviously, as you got further away from the epicenter, the shaking dissipated. So what we felt here in Twin Falls was very, very minor compared to what people in Stanley and some of the nearby towns felt. So whenever we get an earthquake, one of the first things we can is spit out by the computers doing a very rapid analysis of the earthquake is this beach ball diagram here in the bottom left corner. These are called fault plane solutions, and these are really valuable. So the computer can quickly locate the location of the earthquake, the epicenter. It can quickly give us the depth and the magnitude. So those are all important pieces of information. But as geologists, we also want to figure out, well, what fault produced this earthquake? And sometimes, unfortunately, it takes an earthquake to tell us where the fault is. That's actually been really common in parts of California where you have this landscape just covered by urban sprawl and cement and buildings. Sometimes it takes the location of the earthquake and the earthquake occurring to figure out where the heck the fault system is that's responsible for that. And so what's really interesting about this earthquake is that when we get the arrival times of different seismic waves and do some analysis, which I'm not going to go into tonight, we get this little weird looking beach ball looking plot. And what this fundamentally tells us is how the fault moved, or how the rocks moved on either side of the fault during the earthquake. And what this specific one shows is that it shows that the rocks move side to side. So if you take your hands and put them together and then just kind of slide them back and forth like you're trying to warm your hands up, that's essentially the type of motion that we saw on this earthquake, which was really weird because the fault system that's right here at the base of the Sawtooth moves rocks up and down. So the location of the earthquake wasn't too much of a surprise, although it's further north than probably most people would have predicted. But the type of movement that this earthquake produced was definitely a real shocker, that the rocks moved horizontally across the fault rather than vertically or up and down, is something that geologists are still somewhat scratching their heads about and trying to understand. When we got all the aftershocks, and I'll show you an aftershock map here in a second, that helps us kind of figure out where the fault is, because the aftershocks are nothing more than small adjustments along the fault as the fault is adjusting to this new stress condition. So the big earthquake caused the fault to fail, at least along part of it, and now you've just changed all the stress that fault experiences. Excuse me. And so the reorganization of that stress and the tiny earthquakes are just the little adjustments to that fault. And then the last thing real quick here is that, interestingly, this earthquake did not cause any surface rupture. And surface rupture is when the fault actually breaks through to the surface and causes some displacement on the surface. So we would expect to see some sort of maybe cut in the hillside, something move side to side if it was this kind of movement. But as geologists got into this area as quickly as they could once the snow had melted, we've pretty much concluded that it just wasn't quite big enough to produce a rupture at the surface. So here's a different little diagram or map, I suppose, showing where the Sawtooth Fault is near the base of the Sawtooth Range. And just, usually for the most part, it's on the east or the west side of some of the lakes down at the bottom. Although Lake Alturas Lake, it's actually on the east side. Here's the location of the epicenter of the earthquake, so magnitude 6.5. Interestingly, it was a location where we had earthquakes in the past. We had an earthquake in 1944 that was a 6.1. Obviously, at that time, there were not a lot of people living in this part of Idaho, so it probably went mostly unnoticed, except to the seismograph stations and the few people that were in the area. And then about 6-7 months later, a little bit further to the north, was another quake that's more or less considered related to it, because they were very close, not just spatially, but also in time. So probably part of the same fault system. And so we think maybe that the Sawtooth Fault, which you can see mapped here, ending right here, we think that it's pretty likely that this fault continues further to the north. Mapping faults is hard, especially when you have lots of trees and topography. You look for subtle clues to indicate that that's where the fault is. Or the other thing to do is actually excavate a big trench in the hillside to find the fault. And that's, the Forest Service kind of frowns upon that type of thing. And so one idea is that maybe the Sawtooth Fault really does end here and another fault picks up, or maybe this is some sort of continuation along this fault. A lot of times faults are segmented, so it could be that the Sawtooth Fault has another segment that kind of jumps over to this direction and then continues more or less to the north or northwest. Okay, so what other effects did this have? Well, the earthquake was felt, like I said, in communities widespread and also close to the epicenter. Here's a photo of the Fred Meyer in Eagle near Boise. And so it knocked some of the products off the shelf. Luckily, there was no fatalities. There was no injuries that were reported. Even in Stanley, where the shaking was most prevalent and strongest, there was no real damage to infrastructure. So this is an intensity level map here. So this is basically how strong the shaking was felt. And just like you'd expect, the shaking was strongest around the epicenter of the earthquake, and then it dissipates as you move away. But even further away in Twin Falls, down into Utah, up into Montana, over into Oregon and Washington, people still felt it at least kind of a light level. So intensity levels use Roman numerals rather than numeric numbers to designate how intense the shaking is. So near Stanley, it was about a 7.5, which would put it in the kind of the very strong category in terms of shaking. Normally this size quake, had this been in a larger urban area, we would have seen much more structural failures, possibly injuries, and even possibly fatalities. But because it's largely a rural community, we were lucky to escape any significant damage to people. Another map kind of showing the same thing. And if you're wondering where this last map actually came from, this relies on human input. So the seismograph instruments will tell us how big the earthquake is in terms of magnitude, but we rely on humans to tell us how the earthquake felt, what damage was done at their location. And so it looks like if you look here at the bottom of this thing, 32,964 people got onto the USGS website, filled out their brief survey, no matter where they were located. And that's what all these squares are for here, different locations. And based on the aggregate of all those responses, the computer is able to plot up a shake map or a intensity map showing where it was the shaking was strongest. We're missing a lot of squares in the middle here because, as you well know, this is incredibly mountainous terrain and there's not a lot of people in this area. But you can see a big concentration in the Treasure Valley, the Magic Valley, over here into eastern Idaho, and then in some of these other more developed areas as well. So that's sort of a map of where the shaking was felt and how intense. The earthquake shaking did produce avalanches. And so this happened during March, late March. And so it destabilized these steep slopes, no different than a skier or maybe an explosion. destabilizing the snow. So we actually did have parts of Idaho Highway 21 that were shut down for a period of time. You can see the photo down here of the Department of Transportation clearing off some of the avalanche debris from the roadway. So the Idaho Geological Survey got in there within the days after the earthquake to try to document some of the effects that we could see. One of the more notable effects of the earthquake was the loss of a nice little beach and recreational area at Stanley Lake. This is a Google Earth image of Stanley Lake from 2016. So here's the stream that comes into Stanley Lake. It's formed over time a delta. So there's kind of a sandy and gravelly bar, if you will, a delta, a depositional feature that's built out onto the lake. A lot of times people come here in the summertime. It's a nice little kind of beachside, lakeside place to recreate. But this actually, during the earthquake, it destabilized this sediment, and it either liquefied or it potentially slid into the deeper water of the lake, what we call lateral sliding. But what you can see, this was a Google Earth image from just about a month or maybe a few weeks, probably just a few weeks after the earthquake happened. You can see all the cracks in the ice around that same inlet. The complete destruction and loss of the sand. So all that sediment either liquefied from the shaking and sunk down or slid out into the deeper water. And you can see all the cracks in the ice here on the surface of the lake. Another view of the same thing. So this is after the earthquake. Here's the little inlet coming in. And what used to be here was this little recreational area here. You can see the trees inundated with water. And so this area of the lake actually subsided as that wet sand at this point actually destabilized and slid down into the deeper water there. So kind of a bad outcome, but pretty cool still geologically. Other effects of the Stanley earthquake in the nearby region. This one has a bit of a personal component to it. There was a lot of rockfall in the Sawtooth. Now, most of it probably was completely undocumented because no one was there to see it, and no one had detailed photos of every rock face and cliff. That would just be an incredible amount of information, and before and after pictures to compare to. But what we have here is an iconic pillar of rock up at the top of the above Hell Roaring Lake. This is called the Finger of Fate. And this is where it became a little bit personal to me, because in 2019, I got together with a friend of mine who is also a guide at Sawtooth Mountain Guides, and we climbed up this thing. This is a 5-pitch climb. Well, it was a 5-pitch climb. It's about 700 feet tall, but the earthquake changed this climb forever. And what I want you to focus on here, and I've got a couple photos I'll show here, is this summit block. You can see a little sky peeking through there. There's not much scale here, but that block at the summit is probably 20 feet tall by maybe 50, 60 or so feet wide. So it's a big chunk of rock, but it's completely detached. It's not connected to the granite buttress that it rests on. It's probably been detached by fracturing and freeze thaw cycles that have just slowly broken this rock free. Of course, you can probably figure out what happens next. When we had the shaking occur, this thing completely fell off the top of the Finger of Fate. And what's sad here is that the climb, which comes up through this kind of open book here, and then comes up over to the right here, up this nice little thin crack, and then up this last pit. This was the last pitch of the climb, and I'll show you some photos from JP and I's, that's my friend's name, our ascent of the Finger of Fate in 2019. So here's another view. So this was the climb that we went up here to this ledge, then out over here and up to this top. But you can again see that precarious, big, huge summit block sitting on top there. Here's me leading the first pitch on this just beautiful, immaculate Sawtooth granite, this 50 million year old pink granite. Here's JP heading up onto the second pitch in this really nice kind of open book, what we call a dihedral, just this corner system. Here we are at the top of the third pitch. There's that summit block. So it was kind of fun to look at my photos after the fact and be like, oh yeah, actually I took photo of that summit block, even though I didn't know. I was really kind of focusing on that. The fourth pitch comes up a crack system off to the right here. This is a picture here in the upper right corner of JP leading that fourth pitch. Picture here is of me coming up to him, so following that fourth pitch, and you can see some of the just spectacular scenery in the background. Like I showed before, like this summit block's detached, so the way to get to the top of this thing is you actually have to crawl under it. So here's JP taking a picture of himself, a selfie. The summit block's right above his helmet there, and he's crawling through a little space to get to the far side. You can actually see in this photo the rope. This is for me at the belay stance. You can see the rope going right into that cavity there. So that's that summit block there. JP and I had to crawl through that hole, get onto the other side of the summit block to where the climbing's a little easier and you can get up to the top. But when you get up to the top, this was the beautiful view you were afforded. So this is looking, I guess, kind of northeast there. Hell Roaring Lake would be off to the right here. This is just a small little unnamed lake near the base of the climb. But then, of course, we had the earthquake. And after the earthquake, I actually compared one of my photos that I just showed you with a photo that another Sawtooth guide took, kind of zooming in and driving past the Finger of Fate. And you can see this notch here on the left photo is the same as this ramp and notch. So the two arrows are in pretty much the same spot, but what's missing on the left photo, of course, is that large summit block, which was there in 2019, but by the time the earthquake happened in 2020 was gone. So I guess I feel a little lucky that I was one of the last group of people to get on top of the Finger of Fate when it still had its little sort of cherry on top of the summit block there. So these are some photos. Some other folks have climbed up there in the last year or so, and you can see that summit block missing there. This is 2022. And then this is a photo of what the summit looks like now. So where this gentleman's standing, there should be a nice big rock right here, big massive boulder. And you can see that its presence should be there because you can see that the granite is completely stripped away and devoid of any of the lichen. So at this high alpine environment, we get extensive lichen growth on the rocks. But this rock was in contact with the summit block, and so it didn't have any of that lichen growth. And now that the summit block's off, it'll probably slowly start to develop that. Got a nice view of Hell Roaring Lake there in the background. So Finger of Fate is still there, although it's missing its topmost summit block. But other iconic rock climbs in the area did not suffer as kind of fate. This is the Arrowhead. I did not climb this, so I don't have a personal story of it, but this is gone now completely. This collapsed during the earthquake. And then a few weeks after the earthquake, I guess maybe several months, it was summertime, there was another large monolith and a climbing destination called Barren Spire that actually collapsed as well. And there's a kind of a viral video on YouTube you can check out where some climbers actually saw it collapse from the lake below and were able to videotape just the big rubble and debris and dust plume that kind of came down after them. So last couple things here. So this is aftershocks in the area. So folks in Stanley might remember 2020 quite well as the year of instability, I suppose. So here's the primary main shock, the 6.5 earthquake on March 31st. But all these other gray dots are all the earthquakes that happened from that date through the end of 2020. So from the earthquake's initiation on March 31st to the end of the year, you end up with like 2,600 or so earthquakes. And you can more or less now start to see sort of two trends that show up here. There's clearly a north or northwest trending zone of aftershocks that probably more or less parallels the Sawtooth Fault, which is further to the south. But there's also this interesting, more or less east-west trend as well. And so as geologists, we're not sure what that indicates. The faults are a little bit tricky to find, like I mentioned, but it is an area of research and hopefully we'll figure it out. But I think for now, we're concluding that this earthquake and most of its aftershocks occurred on a north continuation of the Sawtooth Fault. But stay tuned, that information could change a little bit. So if you felt like the earthquakes would never end in Stanley in 2020, here's proof that you're right. Recognize though that a lot of these quakes, a lot of these circles are very small, and so the smaller the circle, the smaller the magnitude. A lot of these are like 2s, some of them are 3s. Typically, most people won't feel an earthquake until it's a 3, and even then you've got to be really close to the earthquake location, probably stationary, not moving around or doing jumping jacks or you know, walking or anything like that. So a lot of these went undetected. So by no means did the Stanley residents feel 2,664 earthquakes. They felt a small number of the larger aftershocks, but this gives you an idea of how many aftershocks occurred in the area. If we go to 2021, watch the total number of quakes, because I want to show you how that's declined. So 2021, for the whole year in this area, we count about 1,900 almost earthquakes, again with similar trends, that strong north-south trend, and then a sort of secondary trend that's a bit east-westish. The star here is where Stanley sits, so you can kind of see Highway 75 and Highway 21 is kind of obscured in here, but it pops out over here, but through the earthquakes here. And then finally, this last year, 2022, when we only had 1,200 or so earthquakes. So you can see, so I guess I'm hoping to put at ease at least a little bit for my Stanley friends and Central Idaho friends. The aftershocks are diminishing. They are slowing down. If we take all the aftershocks, and this goes only maybe a year and a half, almost 2 years past the initial earthquake, the red line here is what we would predict. So basically, after the main earthquake occurs, aftershocks are, there's a lot of aftershocks immediately, but as time goes by, so time is this axis here, as time goes by, the number of earthquakes decreases quite a bit. So the red line is what you would expect, and the black line is what we actually observed here in Stanley, or in the Stanley area. And so you can see it closely mirrors the predicted values here. So basically, as I kind of conclude my talk here, what can folks expect in the months and years to come? Possibly an aftershock, but it would be small. The size of the aftershocks are going to decrease, but the aftershock sequence can continue for several years beyond the main shock. And folks in Stanley, you live in a earthquake-prone region. Those beautiful mountains you get to gaze and gawk at are there because earthquakes have pushed the mountains up relative to the valleys. And so that beautiful scenery, I suppose, comes at a bit of a cost, and that cost is living in earthquake country, which just means you just need to educate yourselves and be a little bit proactive. But earthquakes in the future for this area are a given. How long till another big one? Who knows, but you know, likely it'll take some time, years, maybe decades, but no one knows for sure. We saw in 1944, there was those 2 magnitude 6 earthquakes that occurred within 6-7 months of each other. So with that, I've been with you about an hour. So I want to just thank you. I'll leave you with a photo of my better half and I up at Sawtooth Lake this past July 4th. And with that, I will stop sharing. And I'll turn things back over to Jane to see if we have any questions or any comments.
Okay, thanks so much, Shawn. That I think we probably all learned quite a bit. I seem to have lost my chat here. Just wanted to thank Liesl for putting the link to Shawn's YouTube channel, and Kozlowski here has, I'm pretty sure that's a link to Bear Inspire falling.
Yeah, perfect. That's a great little video to watch. Yeah, it's interesting.
So open it up to everyone for questions. You can unmute yourself. Anyone have questions for Shawn? Or you could throw them in the chat.
Shawn, this is Liesl. Thanks. That was amazing. And the fact that you missed the big earthquake by prepping for family yoga night is fairly impressive too. So you're forgiven.
Yeah, bummer. Thank you.
I didn't absorb how the little lakes and tarns are formed. Can you just really quickly tell me, is it the glaciers going sort of forward and backwards and shoveling out a scoop, or I kind of missed that?
Yeah, so if you think of like the snowfield forming initially on the slope, and then the snowfield gets larger and larger, eventually it's ice, and now it starts sliding and scraping along the bottom. So it's excavating that depression. So those cirques are actually formed that's where the glacier originates, right? So it actually starts in that location, probably is small and limited, and stays there. I mean, for some period of time, maybe a few decades or hundreds of years, maybe thousands of years, until finally you've got more ice to move it further down the valley. But those little glacial lakes would just be depressions left by the ice. And then, of course, in the Sawtooth, the reason you have so many lakes, partially as we explored, is you've got a lot more snow and rainfall. You guys steal all the moisture, if you will, from the Lost River Range and some of these other mountain ranges. And so those mountain ranges have the depressions to some degree, but they don't have the moisture content coming from the sky and the precipitation to fill those basins with water and keep the water there year round. Does that make sense? Did I answer that well enough?
Yep, absolutely. Thanks.
Yeah, really good question.
Appreciate that.
There's a question in the chat from Dan Cooper wondering, are the Sawtooth and the Lost River Range similar ages?
Right. Thanks, Dan. Nice to have you here. Well, I'll answer it both ways because I don't know exactly which you're referring to. I think he means the mountains. The mountains are broadly about the same age. Both mountains are produced by the extensional faults that have pushed the mountains up. And so both of those fault systems are initiating around 15 million years ago. It's the same regional event that's producing the Tetons, the Wasatch Mountains, a lot of the mountains in Nevada, the Sierras. It's a lot of the mountains in the Intermountain West are being produced by this period, which is called the Basin and Range extension. So the mountains are about the same age. If he's asking about the rocks are very different ages. The Lost River Range has the much older sedimentary rocks that are around 350 million years old. The Sawtooth have mostly 50 million year old granites that are much, much younger. So hopefully I answered your question, Dan. I sort of had to guess there which way you're going with that.
Another question or comment from Jesse Roughgarden. Is it fair to say the higher you hike in the Lost River Range, the more likely you are to find marine fossils? We observe the little sea worms and shells all the time, but have yet to see fish or any vertebrate. Yeah,
that's a great question. And I need to spend more time in the Lost River Range. That's one of my New Year's resolutions is it's been vastly overlooked by me. I've been to the top of Bora, and that's about it. I've been to a couple other places in the Lost River Range, but I'd like to get up there and explore it more. I would say, to answer your question in general, no, because the rocks are all tilted. And so the fossils aren't necessarily going to be higher. The fossils are just going to be in whatever layer or strata formed at a time when the ocean was a certain depth and biological productivity and diversity was high. So generally, if you look at where organisms live in the ocean, it's in a couple 100 feet of water where there's photosynthesis. That's where we get like things like reefs, coral reefs, all sorts of organisms that live around those coral reef communities. If you go out into the deeper water where it's, thousands of feet deep, there's not as much biological productivity. So you wouldn't see the fossils there, although there are organisms that are just really fine microscopic organisms. So to see the fossils big enough to the naked eye, you would just need to be in the right layer. And because all the Lost River Range rocks have been tilted or folded, however I do that with my hands, there you go. That means that you would want to look for So what you would need if you want to look for fossils and you are just taking a shot at it, let me know, because we could get together some geologic maps and we could look for layers, named layers of rock types that are known to have specific fossils. The second part of her question is that they see little sea worms, or probably not sea worms, actually. You're probably looking at coral, like chain coral, and shells. There's a lot of horn coral in there, but you're not seeing the fish or any vertebrates, primarily because the main organisms growing in those shallow water reef environments, there are fish around at that time in Earth's history, but by far the much more productive organism in terms of making shelly material, hard material that could be fossilized, would be the invertebrates, things like brachiopods, clams, coral, echinoderms, things like that. So hopefully I helped a little bit there, Jesse. Good question, though.
Okay, anybody else? We will send out an email with the link to the recording, and it will also be on our website. So watch for that. And unless anyone has anything else, I'm going to stop the recording and we'll call this a night. Thank you so much, Shawn.
You bet.
Also,
Thank you.
If you would email me your mailing address, I'd sure appreciate that.
Okay, no problem. Absolutely. Thanks everyone for joining. Have a good evening.